Andrew with HKN, and today we're going to be talking about another tree algorithm, and this one is called Dijkstra's algorithm, not to be confused with DJP, which we did last week, which is Dijkstra Prim. This is just one guy, this is Dijkstra. And this one's a little bit different. It's not exactly a minimum spanning tree. What I like to call this is the minimum routing path. So in this case, what we do is we're going to have our same tree that we've been working with, but what we're going to be looking for is we're going to be looking for the shortest delay path that we can find from A to every other node. And so what's nice about this is that we'll get, when we're done with this, when we run the algorithm, we'll find which path to take to find the shortest path from A to B, A to C, A to D, and so on and so forth. And there should only be one path from each. But what's nice about this is we can then run this on each node consistently, and then each node would have its own protocol about which way to go to get to any other node, and they would be independent and also optimal. So what we call this is this could be called a distributed algorithm, which means you don't need a central person like me or a central node like a master node to dictate how everything in this thing will run. Each one can run this algorithm by itself and still be optimal in the end. So that is something that's nice, because then you don't need to worry about communications from the master to everything. Each thing is independent, and I believe it's also pretty power efficient. So what we're going to do is we're going to start with Dijkstra's algorithm. So we're going to initialize everything to be an infinite distance away from our starting node. So what you'll see down here is you'll see the current process that we're doing. And over here, what you'll see is we have a visited list. Once everything has been visited, we are done. And once something has been visited, you don't have to worry about its weight anymore for adding it to our minimum routing path. And we're going to keep a track of a list of the edges that we're using, and we're going to keep a list of the updated node costs. And this is just the possible vertices we have. So starting at A, what we're going to do is we're going to add things that are at least one distance away, similar to DJP. We're going to add things that are one distance away, one node away from something already on our minimum routing path, and update their weights. So what you'll see here is that B is a distance 1 away from A, D is a distance 2 away from A, and so we update those. The next thing we do, again, very similar to DJP, is we take the smallest non-visited node already and add it to our minimum routing path. So again, that's this top one from A to B. And so B gets added, but we don't, unlike DJP, we don't update this to 0 now. This stays as 1. And what we do is we update all adjacent nodes with their distance not from the closest node. So in DJP, we would update F now because B has been added. We would update F to 4. But in Dijkstra's algorithm, that's not what we do. We update it with its distance, its smallest distance to A. So it doesn't get 4 now, it gets 5, because the shortest distance currently it can take to A is 4 from B to F, and then 1 from B to A. So what we do is we update that to 5. And from here on out, we're going to continuously do this. So we're in the update phase, and now we're going to add edges again. So what we do is we add this one because it is the smallest number. 2 is currently the smallest number in our node cost list, and that is from A to D. So from A to D, we add this in here, and then the next thing we're going to do is we're going to go to the update phase, and we're going to update C, G, and E with their distances from A. So if D is 2, the distance from D to C is 2, so that gets a 4. D to G is 4. 2, so plus 2, so it gets a 4. And then D to E is 4. D is already 2, so it gets a 6. And we're just going to continue on like this. So we add the next smallest one. That's just kind of random again because these have the same weights. Just pick C because it's first in alphabetical order. Like it really doesn't matter. Usually you'll just kind of search down the list, and the one that comes first in your list, which will normally be in alphabetical order if you initialize it like that, will be seen first. So we're just going to go with that. So we add that and we update. So this could be updated to a 7 possibly, but 7 would be larger than 5, so we don't update it. And so then the next thing to do is to add the G here, which is a 4, which this could then be updated to a 5 from down here. So what that tells us is that we can get to F from G or from B, and it'll cost the same to get there from A. So it really doesn't matter which one we add. So what we're going to do is we're just going to add the one from G, because why not? So we add the one from G, and we will then update all adjacent nodes that aren't in the graph already. So that's I. So we update I to be a distance 7 away. The next smallest one that we haven't visited yet, we see, is E, which is 6. So we add that one, and we update all adjacent ones, which in this case will be H and L. H should get a 7, and L should get an 8. So you see this is fairly simple. We're just going to keep working through this. We have E to H here. E to H is probably the next biggest one, or we could do F to I. They both have 7, and again, it doesn't matter, so we're going to add E to H. We add E to H and then update the next closest ones. So we could update I to be 11, but 7 is shorter. We could update K to 9, and we can update J to 11. So we do that. The next smallest one, I believe, is 7. And that could happen from either H to I, so we could add that, or we could go from F to I. And in that case, we're just going to go F to I, because why not? So we have that added in, and we end up with where we can update M here. So M can be updated to 11. The next thing we're going to do is we're going to add 8, because that is the next smallest one. So we add that in, and we can update K to be 11, but we don't need to. We can also update N to be 11, and we don't need to either, so nothing gets updated. The next thing we're going to do is we add 9. That is the next smallest one, and that comes from H to K. So from H to K, we can then update. So we could update M to be 12, but again, we don't need to because we can already get there with 11. So the next thing we're going to add is we're going to add the this one here, which is H to J. But like what we can see here is we could also have gotten there from above here, from at I. So it would have been an equal cost to get there from there. It doesn't really matter. So we just pick one, and it should be the same. We update, but again, there's nothing to update. So we're going to move on again, and we're just going to add our last node here, M, to our list. And again, we could have gotten here from above as well. That would have also been with a cost 11, but it doesn't really matter. So we're done. We can see that we've visited all of our nodes. We have a list for the distance to all of them from A. And so now A knows which path to take to get to any other path. And you can see it kind of makes the tree similar to like our minimum spanning tree. But the interest of this tree is different than the interest from the others. The minimum spanning tree gets you the smallest cost to traverse the whole tree. The Dijkstra's algorithm is finding the minimum cost to route from A to any other point in the tree. It has a specific starting point, and these numbers are only valid for that specific starting point. If we picked somewhere else to start, we would get the minimum routing from, say, B, and all of the numbers updated would have the cost to get from B to everywhere else. And you know that this is terminated when your list has been all visited. Again, I do this little table over here so you can kind of see how you would keep track of things and how an algorithm would work in a computer or something like that, because that is where these are meant to be implemented. So I hope you guys learned something about Dijkstra's algorithm today. I hope you learned something about all the tree spanning algorithms, the tree traversing algorithms. I think they're very interesting. And if you have any questions, leave them in the comments below. And I hope you learned something. See you later, guys.